Hello. So in the last lecture, we learned interval estimation. I derived how to construct a confidence interval, and the main key idea is the trade-off between confidence level and the margin of error. So the confidence level is the probability that your interval is correct, and the margin of error is literally the margin of error. So an ideal interval estimator would have a high confidence level and at the same time small margin of error. But obviously, if you reduce the margin of error, then you have to sacrifice the confidence level. Or to increase the confidence level, you have to widen your interval, so the margin of error should increase. And then to overcome that trade-off, we have to fix one of them, and usually we fix the confidence level, the percentage of correct estimation. So usually we use alpha for the error probability, then the confidence level becomes 1 minus alpha. And then given the error probability alpha, the confidence interval takes this form. To derive this, also the main idea is the normal approximation of x bar from the sampling distribution chapter, right? We know that x bar is normally distributed, so using the normal distribution knowledge, using that, we make an interval that contains 1 minus alpha probability, and then recover the margin of error according to that. And then in the end, the formula is pretty simple. X bar, which is a point estimator, and plus minus margin of error. This much is the margin of error, which depends on standard deviation and the sample size, and z-value. This is top alpha over 2 probability value from the standard normal distribution, which is given here. So simply, these confidence level imply these z-values, right? Or you may use a calculator table, or if you look up any statistics textbooks, you should be able to find how to obtain this. And I explained that in chapter like 6 when we did some exercises on the standard normal distribution. So anyhow, calculating the confidence interval is simple, but you need some practice. And I gave you an example, a pretty simple example about, say, cost of like COVID-19 treatment. Say, for example, in this case, it's pretty simple. We only know the number of patients and their average expense and their standard deviation. You can calculate the average, simple, and you can calculate the standard deviation, like simple. So, and then what you need is just name your confidence level. Say whatever level you want, say 99% for example. If you want 99% confidence level, then using 1, 2, 3, 4, these 4 components can make up a confidence interval. But what you need to do is to transform 99% confidence level into the z-value. So 99% confidence interval implies 1% error probability. So each side has an error probability of 0.5%. So you have to find the point that is 0.5% from the top. That is calculated this way, right? So this point is has the cumulative probability of 99.5%. So 99.5% is below this point, and only 0.5% is upper, greater than this point. Then the calculator will tell you 2.58. So then it's simple like algebra. Just use average and the marginal error. Calculate the marginal error using the z-value, standard deviation, square root of sample size, and subtract and add and subtract the marginal error around the sample mean, which is the point estimator. Then in the end, we obtain the confidence interval like this, right? So about $18.7 thousand up to $21.3 thousand approximately, something like that. Okay, then also I want you to try. We did it last time, and you could obtain the confidence level, confidence intervals depending on the confidence level. So if you change the confidence level, the resulting confidence interval should change too. That's obvious. And at the end of the last lecture, I talked about this. What we want is, like as I said, higher confidence level and smaller marginal error. And I said they have a trade-off relationship. However, there is one way. There is a way to achieve both of them. That is to collect more data. If you have more information, you can do better in every dimension, right? So collecting more data is a possible way to improve on both dimensions. We are going to study that. So by the way, to do this, of course, you have to so this is related to experiment design or survey design. So before starting the analysis, like before collecting the data, you have to think about the accuracy that you want to achieve. That's what we are going to do. So now, like okay, in the previous example, we considered 99% confidence level, and the margin of error was this much, like about like $1,209. So now then just think about this. The margin of error is more than $1,000. This may be too large. You have to think about too much potential errors to manage your finance. Like for example, you are in an insurance company. Insurance company has to manage their fund, and like some should be invested and some should be reserved to pay for the claims. So accuracy of estimation is very important for the profit. Then what I want to do as a CEO, I'd like to make the margin of error smaller than $500. So now the margin of error is like it's nearly $1,300, which is too large. So then we have to reserve too much money for the worst case, for potential claims. But if we could reduce that reserve, then we can make more profit by investing those funds. So what you want is, I would like to make the margin of error smaller than, or at most $500. Still, I don't want to lose any confidence level. Confidence level should be 99% to be safe as a financial institution, insurance company. Then, as I said, to achieve both of them, it's possible, but you need more samples. You need more sample size. What is the minimum required sample size to do them? That is my question. Here, so then let's think about this. It's not that difficult actually. What you want here is the constraint you have here is the margin of error equals this guy. The margin of error cannot be greater than 500. So $500. There is one inequality. And also another restriction is alpha. So alpha is 99%. So this is fixed. So this is fixed, and then what we need, and this is fixed, and the standard deviation does not change. It is what you calculate from, it is given, right, from the data. And then you can isolate, you can solve for n. So fixing this and this and bounding the marginal error by some number, then you only have one unknown, which is the sample size. So that's how we solve for the sample size, minimum sample size you need. And then, like, because the confidence level was 99%, then this z value is automatically 2.58. It follows. We calculated 2.58 earlier, and standard deviation was also given 5,000. And then, what is the square root of n? What is so we are looking for the minimum sample size that satisfies this inequality given those numbers, right? And then it's a math. So this is the marginal error given the confidence level and standard deviation. This marginal error equal to or smaller than or equal to 500. And then moving around the terms, move 500 to this denominator and multiply square root n on both sides. You get square root of n should be greater than or equal to this guy. You can calculate that. It's a number. So if you calculate that, and then to remove the square root, I will take square on both sides. Just take square on both sides, then in the end you have n on this side and this squared on the other side. So calculate that. It is 665.64. But sample size cannot be a fraction, so it should be an integer. So the whole number, the minimum natural number that satisfies this inequality is 666. So that is the minimum required sample size for the desired accuracy. So the insurance company has to spend more money on collecting information, collecting the data this much. This is how we design a survey or design an experiment. So here is another question you can try. So the same situation. The mean is 20,000 and the standard deviation is 5,000. Now I'd like to do it even more accurately. So the confidence level does not change. It's still 99%. I would not sacrifice this. But the margin of error should be smaller than or equal to $300. What is the required sample size to meet those two constraints? Pause the video and try this by yourself. It may be a little bit difficult at first, but you can peek the other slides. So look at the slides earlier about how to calculate the margin of error, and then follow the algebra that I did. And you can use calculator and whatever you want. Try to answer this question by yourself. Okay, I will show you how to do that. So the margin of error takes this form. The standard deviation is 5,000 and should be smaller than 300. And this z value is known to be 2.58. So everything is known but the sample size. So then our goal is to isolate the sample size n on the left hand side by moving the terms, and then squaring by taking squares on both sides. You have n, simply n, which should be greater than 43 squared, which is 1849. That's the answer. So as you can see, because this is much more accurate, so margin of error is now $300, and previously it was $500. So you are making the estimator more and more accurate. So $300 margin of error this means, so you would not allow margin greater than 300. For example, I like error. You cannot allow error greater than 300. So you have to make the margin of error smaller. You have to make errors smaller. So you need much more sample size than before. So the answer is E. Oh, okay, so this is how we design a survey, design data mining. And as you see, this is the starting point. If you in the advanced levels, there are different theories and different things to consider. But I just wanted to show you the very basic setup for like experiment design. In the next video, I will give you another example, which is about presidential election. It is real data. I'm using the real case in the past. So see you in the next one. Thank you for watching. Bye bye.